All right, is the audio okay? Great. I'm Doug, and I'm delighted to be here. I want to thank the organizers for putting this together. I'm sure it must have been a lot of work, but I don't anymore take it for granted when we have opportunities to get together and talk science and share ideas. After 2 years of being out of it, the value is tremendous. The value is tremendous. So it's great to be here. I've never actually been to England before. Maybe it was the language barrier that kept me out. I don't know. It's great to be here. It feels like a tough thing to follow Peter, however. We'll see how I do. I'm going to tell you about some experimental work and some accompanying simulations. The experiments were done at the University of Rochester, and the simulations were done by a collaborator, Declan, from University of New South Wales. And we're thinking about dynamics of flow structures. Maybe I don't need to motivate much, but here's the solar panel array on top of the gym at the University of Rochester. We got a $1 million grant from the New York State Energy Research and Development Authority to put it up there, and we're very excited it's up there. But of course, it's not sunny all the time in Rochester. It might be sunny more than it is in Cambridge, but it's not sunny all the time, and so we need storage. And that's what we're all talking about now. And Don has really inspired us to think hard about liquid metal batteries and how they might really affect electrical grids in a big way. And my question has always been, how does fluid flow affect battery performance? We're hearing plenty of discussion about that today. And one short answer is general flow accelerates transport, which is good because it allows you to charge and discharge batteries more quickly, prevents side reactions, and so forth. But violent flows can rupture the electrolyte and trash the battery. And it's worth thinking about what mechanisms drive flow most strongly. Tom and I wrote a paper a few years ago where basically the paper's just a list of what are the mechanisms and how much do we think they matter. Best guess at the time. And there are a bunch of mechanisms in there, and I commend you to that list. I'm going to talk today about 3 mechanisms. And the first is electrovortex flow, which has already been discussed. So I'll skip the math and just say anytime there are diverging currents, which is almost certainly the case in a liquid metal battery, they create electrovortex flow. And as was stated earlier, the primary flow, I suppose, tends to be colloidal, like this nice visualization from one of Fietz's papers. So that's the first thing we're interested in, electrovortex flow. The next mechanism we're thinking about is convection. Of course, if you heat a fluid from below and cool it from above, buoyant forces cause flow, and you get thermal convection. Here's an image from some prior work of John Chang, who's first author on all this work. And I want to commend John for the work. He really spearheaded all of what I'm telling you about, and he does beautiful work. And he's on the faculty market this fall. I recommend him. Anyway, thermal convection can drive flows in liquid metal batteries because these things are hot and you get thermal gradients. And we can quantify the tendency for thermally driven flows with a Rayleigh number, which we can define this way, and of course it's dimensionless. Really, it's a ratio of buoyant forces to diffusivity. We can also think about compositional convection. That is, the density of the fluid can be changed not only by heating or cooling it, but also by the chemical reactions that are taking place. So if you, say, pull lithium out of solution at the top of a body of fluid, what's left behind is also almost certainly more dense because lithium is number 3 on the periodic table and is going to sink, right? And you can drive flows this way. And in fact, in liquid metal batteries, flows due to compositional convection are likely to be orders of magnitude stronger than those due to thermal convection. And the folks in Dresden really illustrated this nicely in some recent publications. That said, well, whatever structures you get out of convection, we expect will depend strongly on the shape of the vessel. So if you have cylindrical vessels, or if you have box-shaped things, you're going to see different flow modes. Here are some illustrations from a recent paper of Declan's and a paper from a bit longer ago. So we're very interested in shape, and how does shape affect the flow? My third and final mechanism I'm going to mention is stable stratification. So if instead you cool your fluid from below and heat from above, well, the heat makes the fluid at top less dense, and it tends to stay there. So this imposes a stabilizing tendency, and that can interact with other drivers and flows. So, okay, during the charge of a liquid metal battery in the classic three-layer form, pulling lithium out of solution, as I said, and so right here, the material becomes more dense than it used to be and is going to sink. And so during charge, you get strong compositional convection. But during discharge, you're doing the opposite. You're adding lithium right here, which makes this fluid even less dense than it was before. And so it does not tend to sink. In fact, it resists any vertical displacement, stabilizing the flow. And so one thing we wonder is, how does that interact with electrovortex flow, which would tend to cause vertical motions? And so thinking about these three mechanisms, we designed and built an experimental device. It looks like this. It's cylindrical. We use liquid gallium as our test fluid. It has a 10-centimeter diameter. We have electrodes top and bottom of different diameters such that there is diverging current, and we can drive electrovortex flow in this gallium layer. We also have heat exchangers top and bottom. We can control the two temperatures independently. There's two different chillers. And so we can heat the bottom and cool the top in order to drive thermal convection. Or we can heat the top and cool the bottom in order to stabilize flows and look at interaction with electrovortex flow. And by the way, I told you earlier, thermal convection is very weak compared to compositional convection. But thermal convection is a lot easier to induce in the lab. So we built this device to do thermal convection. We expect that if the Rayleigh number for thermal convection matches the Rayleigh number for compositional convection, flows would be very similar. So we believe it's a reasonable idea to model compositional convection this way. And as I said, we're interested in shape. So we built 4 different sidewall pieces of different heights, all the same diameter. So we can access 4 different aspect ratios, gamma, from 1.4 to 3. And we thought a lot about how flows might vary with aspect ratio. To find out, we, of course, added some instrumentation to the device. We have thermocouples to measure temperatures at multiple places in the top and bottom plates. So in the boundary, not in the fluid itself. We didn't want to perturb the flow. But we do measure the flow itself. Oh, yeah, there's some thermometry for you. We do measure the flow itself using ultrasound velocimetry. Ultrasound works like sonar. A probe makes a beep and listens for echoes. If an object there is causing the echo, then from time of flight, you can determine the distance. And via Doppler shift or cross correlation, you can determine one component of the velocity. If there are many objects making echoes, as is typically the case in liquid metal, then with one beep you can hear many echoes and you can get a velocity profile. So that's what we did. I want to commend my PhD student Bitong Wang here. He did a whole PhD looking carefully at the mechanisms by which echoes are caused in liquid metals. So we didn't add any tracer particles to cause echoes. The oxides present in the liquid metal are sufficient, and Bitong looked very carefully at how they act and how to optimize ultrasound signals, and it really helped our data. And his analysis of that you can read about in this paper. Okay, so we have ultrasound probes. We stuck in 9, and we use the ones for signal processing, and let's see, what else do I need to tell you? We chose their positions fairly carefully. We had in mind that electrovortex flow typically causes poloidal motions. We've seen the swirling motions of the sort Frank was talking about at higher currents, thermal convection. We tried to put probes in places that would break all the symmetries and allow us to distinguish those shapes. This apparatus is described in detail in a paper in Experiments in Fluids from earlier this year. Okay, some data. Here's some example ultrasound data. Again, one component of the velocity. I'm showing that in color here. And the distance from the probe is on the horizontal axis and times on the vertical. So by making many beeps over 300 seconds, you can get many measures of velocity along this one line. You can see there's some oscillation here. Another way we can visualize the data is like this, where I've drawn you an arrow at the location of each measurement. Okay, not all the measurements. I downsampled. There's too many measurements. But I'm drawing arrows for measurements here, and their size and color indicates the instantaneous speed. This is played real time. And so you can get a sense for the three-dimensional structure of the flow by staring at movies like this. You can stare a long time. One thing you might ask as you're staring is how the speed varies with Rayleigh number. So this flow is driven by thermal convection. And we can quantify that with the Rayleigh number, and we can quantify the speed with the Reynolds number, of course. Speed times size over viscosity. We chose to use the speed at this point near the middle of the apparatus where the beamlines of 3 probes intersect so that we can measure all 3 components of the velocity. Constructing our Reynolds number that way, we went and did a bunch of experiments. So each of these circles is one experiment. And calculated the Rayleigh and Reynolds number for each. You can see, for starters, that among the aspect ratios we considered, the speed is actually not affected that strongly by aspect ratio. Gamma equals 1.4, 1.7, 2, and 3 all fall nearly along the same trend line. We can fit a line to that. And it turns out its slope in this log-log plot is 0.43. That's pretty close to a number of prior studies and also pretty close to the 0.4 prediction from Allers and company theoretical. So that's good. That's a nice sanity check. But we did find it pretty interesting that aspect ratio just doesn't affect things much, at least for speed. It does matter for some other things. Here's that data again. If you stare at the movie a little longer, you'll certainly notice that the flow is oscillating. It is not steady, and it's got some periodicity to it. We got interested in that, and so we calculated power spectra. At top is one calculated from a thermocouple on the bottom. At bottom is power spectrum from an ultrasound probe. We use the whole field of view of the ultrasound probe, average spectrum over time. And you can see there are some very clear frequency peaks. This is at aspect ratio 1.4. At other aspect ratios, we see similar peaks. Here I'm marking them with vertical lines. I got a solid white line for the lowest quite strong peak. The dashed white lines are harmonics of that. And the yellow lines are a different strong peak, which is not one of the harmonics. So we think it's a different phenomenon. And though here I've shown you just one thermocouple and one ultrasound probe, we see similar frequencies across nearly all our probes. So these frequencies would suggest that there are particular flow structures. We wanted to find out what those might be. And let me talk first about the frequency marked in white. To explore it, we phase averaged around that frequency. So it's about 0.03 hertz. We took long sequences of data and divided them up into intervals of 1 over 0.03 hertz and averaged. And when we do that, we get flow that looks like this. You can see a counterclockwise circulation. That's the large-scale circulation, which you expect in thermal convection. You can also see it's oscillating over time. And if you stare at this long enough, perhaps I can convince you there's a clockwise orbit of the vortex core. The fastest bits, where the arrows are biggest and most colorful, tends to orbit in a clockwise direction through the course of this oscillation. You have to squint your eyes a little bit to see it in the experimental data. It is what it is. We have only so many probes. But going to simulations allows us to look at things in much more detail. And so Declan did some really great simulation work in collaboration with us. He used OpenFOAM. He built a really nice solver. Here's more details about it. Maybe I won't speak about them at great length, but I'd be happy to talk more if anybody's curious. And what came out looks qualitatively, at least, like what we see in experiments. You can see large-scale circulation in the same direction. Similar structure when viewed in plan form as well. And when we look at a cross-section through along a diameter, we see this similar structure again, where there's a counterclockwise large-scale circulation with a vortex core that orbits clockwise. And that structure is consistent with what was called the jump rope vortex in a recent paper out of Tobias Vogt and others, John Arno's team at UCLA, which looks like this, where it's an oscillation of the large-scale circulation with this particular shape. Looks a fair amount like ours. To understand it more deeply, we looked at the frequencies in many experiments. So again, here, each circle is a different experiment. Well, that's the velocimetry. We have stars for thermometry in many experiments as well. This is Rayleigh number on horizontal and frequency of this particular oscillation mode on the vertical at various aspect ratios, and also for the data in that 2018 paper. You can see a similar trend, which supports the idea that, yes, this is the jump rope vortex. It also begs the question, what sets this frequency? Clearly, there's a systematic variation with Rayleigh number. And it's different for the different aspect ratios in experiments. What sets the frequency? You might take a guess that since we're talking about thermal convection, heat at the bottom, chilling at the top, the distance vertically, the height of the cell, would be important. And you might wonder if the thermal convection time, the vertical thermal convection time, vertical thermal diffusion time would set the frequency and cause all those curves to collapse. We tried that. And it brings the UCLA data a lot closer to ours, which makes sense because their apparatus is a lot bigger than ours. Scaling out the height would help. But it doesn't really collapse very well. However, if you instead think about the loop distance traversed by the core of that jump rope vortex, 2 heights and 2 diameters, the data collapses quite nicely along different aspect ratios and different experiments. So it seems that that's the distance which sets the frequency that we observe in experiments. Okay, here are those spectra again. The lower frequency seems to be the jump rope vortex. Now I want to talk about this somewhat higher frequency marked in yellow. To explore it, we ran a bandpass filter. Because the signal associated with the jump rope vortex is much stronger, in order to see this at all, we needed to filter that away. And so we did a bandpass filter around 0.055 hertz. The resulting data looks like this. You can see the spatial structure is quite different than that of the jump rope vortex. And I want to pull out just 2 probes, 6 and 7. These 2 are not on diameters, they're on chords, so they're offset from the center, horizontal. And if you look at them here, they almost always measure velocities in opposite directions. And that's consistent with the torsional oscillation of the large-scale circulation, which Frank mentioned earlier. Here's another diagram of it. Yeah, it goes back to a 2009 paper, and so as the large-scale circulation is going along, there's a back and forth. I'm not sure I can do the dance right, but okay. This is another known oscillating mode of the large-scale circulation. We looked deeper with the idea that maybe this was it to see how well the data supported that idea. So here I'm showing you spectra from those same 2 probes. The original spectra are in gray. The spectra after filtering are in orange. And after filtering, we can look at more than just spectra. We can look at the whole signal as filtered. Here's what that looks like. You can see periodicity. You can see sort of diagonal structures in these space-time diagrams suggesting wave motion or wave-like motion. And in fact, if you stare closely, you can see that, yes, the 2 probes really are 180 degrees out of phase almost all the time, almost everywhere, and at the same frequency. So we think that's pretty good evidence that this is probably explained by the torsional mode. I talked about electrovortex flow. I haven't told you anything about electrovortex flow yet. This is ongoing work. We've done a bunch of experiments. We're analyzing data now to understand what's in it. The electrovortex flow can be quantified by this electrovortex parameter S, dimensionless, depends on current, density, and viscosity. One thing we did is just plot Reynolds number versus S in a series of experiments. Here's what we get, and when we fit a line to the data, it has an exponent of 0.52, which is consistent with the prediction from theory from a number of years ago that the speed should scale as the square root of this parameter. so that we think that's a good confirmation. When we look at the actual structure of the flow and measurements, things get more interesting and complicated. So here for aspect ratio 2, I'm showing you measurements from 2 different probes, number 3 and 4. And this is with Electrovortex parameter 2 times 10 to the 3, so this is quite a low current. This is 5 amps in our system. And when we compare those plots and this spectrum to the thermal convection data, they're very similar. So with low current, we do indeed, as you would expect, see that the current has little effect, and the flow, when the current's combined with heating from below and cooling from above, basically is just doing thermal convection. However, we ran some higher currents, 2 orders of magnitude higher interaction parameter. This is 60 amps in our apparatus. And here, the structure is very different. It's different spatially, as you can see at left. It's different temporally, as you can see in the spectrum. The jumper vortex spike is gone. The torsional spike is gone. Clearly, the flow structures have changed a lot. And I hope soon to be able to tell you in more detail what's going on there. That's where we stand now. We're looking a lot at those flows. Okay, so that's most of what I wanted to tell you. We've done some experiments. We have seen that jumper vortices and torsional modes appear on the large-scale circulation in liquid metal batteries, or at least in devices meant to model liquid metal batteries. The dependence, I've been talking a lot about shape and aspect ratio. The dependence on aspect ratio is pretty weak until it's not, is kind of what we found. Remember, the Reynolds number scaling was pretty flat. And the jumper vortex was present for all of our aspect ratios except 3, when we made the device quite short and wide. And then basically you destroy the single large-scale circulation. And that changes everything. So that's when shape really starts to matter a lot. But until then, it doesn't matter much at all. We're doing more work on electrovortex flow. And you can read more about this whole story in a paper with John as first author, published in JFM this year. And finally, I just want to thank my research team. Here's the folks I work with every day, and they make it fun to come to work every day. I should say, Don mentioned the importance of surface tension in confining metals in liquid metal batteries. I haven't talked at all about surface tension today. I think it's interesting. We've got a project looking more closely at surface tension. That's ongoing work. I don't have any results to report yet. But Ethan is working on that, and I'm excited about it. And the other thing I want to say is I have opportunities for PhD students, postdocs, and a data scientist. So if you know anybody who's looking for work, I am looking for people and would love to talk to them. That's my story. Thanks for your time.
Scaling you propose for your frequency, your jump frequency. Did you try? I was expecting that you would try the advective time scale. So in the third plot, like rather than scaling it with the loop diffusion time, have you tried to? Because the idea is that anyway, there's a circulation. So if you have this is like an advective time scale, like h over u. So you would expect if there's some oscillation, it's going to go through the cell at this frequency. So this would be like typical for other flows too. It's like a Strohal number, which is going to be some value that is fixed. So I would try to rescale everything in terms of an advective time scale.
That's an interesting comment. I don't think we've tried it. I was trying to remember what the Kelley number is and how similar it would be to the diffusive time scale, but I can't remember off the top of my head. Yeah, let me look at that. Let me look at that. Thank you.
You mentioned that compositional convection is likely to be much more important than thermal, but you said you take thermal as an analog, assuming that it's the same Rayleigh number, behavior would be similar. Of course, the difference is that for thermal convection in gallium, the Prandtl number is much less than 1, or substantially less than 1, whereas for compositional, it's probably substantially larger than 1, and I would expect this has a strong effect on the kind of pattern and instabilities that you observe.
Thank you. That's an interesting point. I'd love to talk more offline maybe about ways to get around it or ways to make the most of what we can do.
Yeah. Very interesting talk. So when I looked at the pictures from Jonathan's presentation at APS last year, the question I had in mind was, which electrode are we trying to simulate here? Which electrode that we are trying to experiment with? Is it a negative electrode because the current is diverging from the top? Or is it the positive electrode because you mentioned convection?
We're thinking mainly about the positive electrode, yes. And we expect convergence there, divergence there as well. You know, the negative electrode is pretty well confined by a metal foam and can't flow much.
So this is a positive electrode with a converging current at the bottom? Because
no, but the divergence that comes from you've got divergence even in the positive electrode because the negative electrode is small. Yeah, I guess that's the
so
answer.
it depends on the size of the metal foam versus the diameter, I guess.
Right, exactly.
Yeah, okay. And a comment from Professor Uli's comment here. So when we do thermocompositional convection in dynamos, they define a common parameter which would represent both convections. But it becomes difficult because of the magnetic Prandtl number and also because it's not like the double diffusive situation where we can combine both into a single parameter. They have to be looked separately. I had the same thought earlier where I was tempted to simulate the thermal convection and also talk about compositional convection as a proxy, but I think it's not so straightforward.
Thanks for that. My question was just about you have talking a lot about oscillatory or orbiting motion throughout the whole cell. And I was just curious if you know or if you could speculate on, does that have a net good or bad effect on transport of your itinerant ion through the thing to help out your voltage at all? Or does it all cancel each other out?
I would expect that oscillatory motion would promote mixing and thereby facilitate faster mass transport, faster charge discharge, at least at this level. You know, these flows are slow enough; they're not going to break through the electrolyte layer.